So good morning, everyone. I will welcome to this presentation. I will describe experimental validation that was made to validate underwater source localization, and is based on cylindrical near-field holography. Okay. In this case, on a submarine. Okay. This presentation, there were a few partners involved, OROS of course, and a few partners from China, and in particular the China Chip Research and Design Center. So first, what are the objectives of doing this? First is to check the acoustic stealthiness of defense ships and to make them unrecognizable by potential enemies. Okay. And also eventually, but that's usually a minor impact for them, to reduce the impact on the underwater environment. Well, mainly when maintenance and upgrades occurs on ships, this may introduce some modification in the source and acoustic emissions. And so that's typically where people who want to do this is typically before and after to check that is there any, let's say, a new noise created by those changes. Okay, so typically this is introduced by machineries in the ship. So the methodology is done in two steps. First, there is a measurement. It's a near-field acquisition close to the ship, and usually with this ship standing still, so in the dock. Then there is a post-processing, okay, based on this choreo data, and it's there is two main steps. The first step is a near-field localization and characterization of the field, and then a far-field process is also possible to check the impact at the longer distance. Okay, so the typical instrumentation used for that kind of measurement is typically teledyne RESON hydrophones. So it's not only one, it's based on an array measurements. So typically, let's say about 20. In this case, we have 90, but 25, sorry, 25. In this case, it's a typically curved or segmented hydrophone array, and they are placed at different intervals. And then there is a scanning setup to cover the area of interest in the ship, because you could not afford to have, let's say, a complete hydrophone array covering the whole area. So you need a kind of scanning setup to do it. Okay, and then you need a typical acquisition instrument to acquire and first do a pre-process of the data, typically spectra and cross-spectra. So you see here some pictures of a typical array and instrumentation. So you see, so it's quite a heavy setup to build. Basically, in this case, is some pictures taken on an Australian ship, where you need basically a array to scan the whole structure. Okay, you see the hydrophones here. This was taken in France at DCNS, now naval. So then comes the post-processing. Once you have done the acquisition, you need to do the post-processing. That will bring a number of informations. First, the characterizations of the sound sources. So typically the frequency analysis, because all this is dependent on the frequency that you want to look at, and that will also help you to get back to the machine that is involved in the creative noise. The main result of this also is basically a map, an acoustic map with scaling colors to know where the sound comes from. Okay, and this can be given either based on sound pressure, particle velocity, or sound intensity. the second step is then to have the quantitative analysis of the noise, not only the localization, but how much noise does this particular spot radiate. Okay, so in order to be able to compare this result from one measurement to another, you will need to do this. Yeah, and then you can also rank sources by defining spots and deciding which one is the highest contribution. Later step, you can do a far field radiation noise, so that will basically give you a directivity map of the emission. Okay, and then yeah, that's basically the only underwater NEH solution existing today. So looking at the particular objectives of the project we are looking at now is basically to validate this methodology on a submarine. And in our case here, we are using artificial excitation because for obvious confidentiality reasons, military people cannot afford to leave out signatures of the ships. So that's of course that's a very key information. So in this case, we use the artificial excitation to check that it was correctly located. So a shaker was used, okay, basically mounted at the rear of the ship, and then there was an accelerometer used as a reference sensor. Okay, this accelerometer was placed really near to the shaker. Okay, and this particular measurement was carried out on a hydrophone array based of 25 RESON TC4013 hydrophones. The radius of the array was about 4 meters. Okay, and they were placed at intervals of 3.6 degrees. Okay, then the scanning surface was that the array should move by longitudinally along the ship to form a partial cylindrical scanning surface, about 19 positions of 30 centimeters apart. Okay, and the distance from the submarine was from 0.6 to 1 meter, because the submarine, and especially at the rear, where you have a lot of propulsion elements and so on, is not constant. Okay, so because of setup reasons, it's not possible to change the distance from the measurement surface. So it was considered to have this distance from 0.6 to 1 meter. Okay, so first results. Okay, you see that we can look at the sound pressure measured on the array itself, so on the measurement surface. Okay, so we already see some good results, and we can look at either single frequencies or also octave bands. Typically here 12 octave bands. Okay. So that's the first result. So already makes sense. We also make some checks, okay, concerning first the frequency range, to see, because the shaker is not exciting the whole frequency range necessarily. So we could see that looking at the reference sensor, we had a good excitation above 600 hertz. Okay. And we also could cover that the repeatability at the reference point during the 19 test was really good. Okay. Of course, we should not have any change in the shaker excitation and so on, because otherwise we would make the test based. Okay, so we looked at the pressure on the hydrophone array. That's one thing, but the most important result we're looking at is the back-propagated estimation. We are not looking at the radiation 1 meter away. We want to know what is it about on the surface itself. Okay. So there is a back-propagation calculation, and that's built by reconstructing the sound field in between the surface and the measurement area. And so we also checked, on top of the different frequencies, we also check different distances. So here the calculation is done at 1 meter, and then there is another calculation done also at 0.8 meter to see the impact of the distance. So also you see that at 0.8 meter, it's the localization is very similar. But also we see just that, and it's logical, that the closer you get to the sound source, the greater the level that is obtained. Okay. We also see that here, the result, of course, that is back-propagated is much more accurate than the result of the measurement done on the measurement surface. If you remind, that's the result based on the actual measurement surface, and that's what we get at the back-propagated result. Next step is, okay, now we obtain the sound pressure. Next step is to obtain the sound intensity, because that's what will allow us to obtain finally the quantitative analysis and the sound power. We also see here that the sound intensity provides even more accurate localization of the shaker position. So we could easily interpret that if you had a machine instead of a shaker, you could also locate it like this. So you see also that, and that's actually the sound intensity calculation is a unique advantage of the holography. So next step is sound power calculations. Once we have the sound intensity, we can obtain the sound power, and that gives us really a quantitative analysis of the sound source. We can obtain this result either in narrowband or in octave bands, typically 12 octaves, which give us a very more, let's say, average kind of visualization in terms of frequency bands. And then, of course, in this kind of situation, you may have a number of sources. So when you have multiple sources, you have the need to rank them in order to know which one is the highest contribution. So you can define, in this methodology, you can define areas, and you see there, where you say, okay, now I want to calculate the source power, the sound power emitted by this particular area. So you can do this on the map. Okay, and out of this you will get different sound power, and you can compare these different sound power results. Okay, you can also decide to retrieve this particular area and to see the impact on the sound power, global sound power. So let's say I suspect one machine to be responsible because I have this new spot on my map. I need to fix further this machine to reduce my sound power level. So here, what happens if I do it, or what happens if I put an additional shielding protection to prevent this problem to occur. Okay, so you really have all the tools to do this, cover this application. Okay, next step is the far field estimation. We, based on the same results of what we have done in terms of acquisition, we can basically reconstruct the far field radiated out and get the results at a certain location that is defined. So you see here typical results. You can get the narrow band and the octave band as well. Okay, so and we can also obtain the directivity plot. Okay, so doing this process here in our particular situation, you can see that the shaker was on the left side of the submarine, and the directivity map gave us a good result at, let's say, about 100 meters away to the left of the measured object. Okay, all this is based on OROS solutions for noise and vibration measurement and analysis. So we provide instruments, software, and the service for the marine and transports industries. So, getting to conclusions, okay, by performing a scale measurement close to the surface of the submarine and processing ADH afterward, we could calculate the sound field around the submarine, and parameters like sound pressure, particle velocity, and sound intensity can be easily estimated. Sources can be accurately located and characterized, and also we can process some far field acoustic radiation. Okay, so the OROS Underwater ADH solution provides the basis for this kind of testing, and consequently also reduce the noise emitted by the submarines and other ships as well. Yeah.
Thank you. Thank you.
Teledyne Marine. Everywhere you look.